Welcome to an introductory video on vectors. The goal is to define a vector and also to define basic vector vocabulary. So measurements that involve time, length, area, volume, and temperature are called scalar measurements or scalar quantities because they can be adequately described by their magnitude alone with the appropriate units. And the related number is called a scalar. So for example, when we talk about the temperature outside, if it's 85 degrees, that's enough information to describe how warm it is outside. Other measurements that require more than a single quantity to describe their attributes are called vector quantities. Examples of vector quantities are force and velocity. These require both magnitude and direction to completely describe. So for example, if you're driving your car and you're going 60 miles per hour, you would also want to know what direction you're driving in, so it takes two quantities, a magnitude and a direction. A directed line segment is used to represent a vector quantity, as we see here in black. The length of the vector models the magnitude, the arrowhead models the direction, the origin of the segment is called the initial point, and the arrowhead points to the terminal point. So here we have a velocity vector with initial point A, terminal point B. Its magnitude is 55, and the direction would be heading east. And here's a force vector that's 120 newtons, and you can see the force is slightly upward. You can also label a vector with a bold lowercase letter, and if you can't bold the letter, you should put a little vector symbol above the letter, which we'll see shortly. Vectors are equal to each other if they have the same magnitude and the same direction. So these first two vectors, even though they have the same magnitude, they're not pointing in the same direction, therefore they're not equal. The second pair are pointing in the same direction, but they have different magnitudes because they have different lengths, and so they're not equal. But these last pair are equal because they have the same magnitude and the same direction. A vector with its initial point at the origin, as we see here in red, is called a position vector. A position vector u with its endpoint at the point AB is written using this notation, and notice they use this type of bracket instead of rounded parentheses so it's not confused with an ordered pair, and this is called component form. The numbers A and B represent the horizontal and vertical components of vector u. So notice in black this would be the horizontal component, so we can label this A, and the vertical component is here, so we can label this B. The positive angle between the x-axis and a position vector is the direction angle for the vector. That would be this angle here. Let's go and take a look at this another way. Here we see a vector in red with its horizontal and vertical components in black. As we change the vector, the horizontal and vertical components also change. Again, this would be theta here, and the length of this red vector would be its magnitude. For a vector v with an initial point x1, y1 and a terminal point x2, y2, the unique position vector is vector v is equal to x2 minus x1, y2 minus y1. This is an equivalent vector with the initial point 0, 0 and terminal point as we see here. Let's go ahead and write this vector as a position vector. So this is the point -2, -3. This is the point -4, 1. So if this is vector v, we can write this as a position vector by subtracting the horizontal components. So -4 minus -2 and 1 minus -3. So this would be -2, 4. So if we graph this position vector, its initial point will be at the origin, and its terminal point will be at -2, 4. These two vectors are equal, but the black vector is the position vector. Next, let's talk about the magnitude and direction angle of a vector. The magnitude or length of a vector u is given by through the square root of a squared plus b squared. And the direction angle, theta, satisfies the equation tangent theta equals b divided by a, where a doesn't equal 0. Let's take a look at a problem. If we want to determine the magnitude and direction of this vector, we first have to have it as a position vector, and we do. So now we can go ahead and just use these formulas. The magnitude of u is equal to the square root of 3 squared plus 4 squared. This would be 9 plus 16, or 25, so the magnitude is equal to 5. Before we find angle theta, we should make a quick sketch of this vector so we know which quadrant it is in, because that may affect the angle we find from this equation. This will be our direction angle. So tangent theta must equal b divided by a, or 4/3. So let's go ahead and go to our calculator. We're in degree mode, so that's okay. Inverse tangent 4/3. So theta is approximately 53.1 degrees, which again is our direction angle. Let's talk about the horizontal and vertical components again. The horizontal and vertical components of a vector u have a magnitude of u and direction theta are given by a is equal to the magnitude of u times cosine theta, and b is equal to the magnitude of u times sine theta. Therefore, it follows that we can find the position vector by using this formula. And again, these formulas should make sense, should remind us of polar coordinates. We take the cosine of angle theta, that would be a over the magnitude of u. Solving it for a, we would have magnitude of u times cosine theta. And similarly, the sine of angle theta would be b divided by the magnitude of u. And then we could solve that for b to obtain this equation here. We want to find the horizontal and vertical components of vector v that has a magnitude 34 and direction angle 37.2 degrees. Let's go ahead and sketch this as a position vector. This would be 37.2 degrees with magnitude 34. So we know we're going to be in the first quadrant. The horizontal component a is equal to the magnitude of u, 34 times cosine theta, and the vertical component is equal to b, which is 34 times sine 37.2 degrees. Let's go to our calculator. We're already in degree mode, so the horizontal component is approximately 27.1, and the vertical component would be approximately 20.6. And we can write this in component form as follows. Now we'll look at two examples of determining the magnitude and direction of a vector given in component form. For this first example, we're going to sketch the vector and then use what we know about right triangles to determine the magnitude and direction. For the second example, we'll use formulas for the magnitude and direction that can save us some time. So for the first example, our vector has an initial point at the origin and a terminal point at the point 3, 4. The terminal point would be here. So here's our vector. The direction would be this angle here between the positive x-axis and the vector. The horizontal component is 3, and the vertical component is 4. So the magnitude of vector u would be the length of this vector, and because we have a right triangle, we can use the Pythagorean theorem to determine the magnitude of u. We would have the magnitude of u squared is equal to 3 squared plus 4 squared. So we have the magnitude of u squared is equal to 3 squared is 9, 4 squared is equal to 16, 9 plus 16 is 25. So now we would take the square root of both sides of the equation. Magnitude is always positive, so we have the magnitude of u equals the square root of 25, or 5. And now going back to our right triangle, we can determine our direction, or angle theta, by using the tangent function, which is the ratio of the opposite side to the adjacent side. So we know tangent theta must equal 4/3. Now having a tangent function value of 4/3 is not a value that we'll find using the unit circle or reference triangles, which means we'll have to use the calculator to get a decimal approximation for our direction theta. So if tangent theta equals 4/3, that means theta is equal to arctangent, or inverse tangent, 4/3. And now we'll go to the calculator to get an approximation for theta.
We do want to give our angle in degrees, so let's make sure that we're in degree mode. We are. So we'll go back to the home screen, press second tangent 4/3, close parenthesis. So the direction of the vector is approximately 53.1 degrees. So here's the magnitude of the vector, and here's the direction of the vector. Now for our second example, we'll use the formulas seen in most textbooks. If we're given a vector u in component form, the magnitude of u is equal to the square root of x squared plus y squared. This is just the Pythagorean theorem. And tangent theta is equal to y divided by x. Again, we used both of these formulas in the first example. We just developed them ourselves using the right triangle. So for the second example, the vector has a terminal point of -6, 3, which would be here. And again, we want to find the magnitude of vector u and the direction, which would be this angle here. But this time let's use our formulas. So we have the magnitude of u equals the square root of x squared plus y squared, or -6 squared plus 3 squared, because the magnitude of u is equal to -6 squared is 36, plus 3 squared is 9. 36 plus 9 is equal to 45. So we have the square root of 45. But this does simplify. It has a perfect square factor of 9. And since the square root of 9 is equal to 3, we have the magnitude of u is equal to 3 square root of 5. And now to find the direction, we know that tangent theta must equal y divided by x, which would be 3 divided by -6, or -1/2. So if tangent theta equals -1/2, then theta equals inverse tangent of -1/2. And now we'll go to the calculator, but keep in mind that our angle theta must be in the second quadrant. So we have second tangent -1/2. Notice how the calculator is giving us approximately -26.6 degrees. And this angle is in the fourth quadrant. But that's okay because we can still use this angle to determine our angle, which we know is in the second quadrant. So the calculator gave us this angle here, which is approximately -26.6 degrees. But tangent is also negative in the second quadrant, which means our angle must have a reference angle of 26.6 degrees in the second quadrant. So if this is 26.6 degrees, then we can find our angle. That would be 180 degrees minus 26.6 degrees. So our direction, or angle theta, is approximately 153.4 degrees. So this example is a good reminder that even if we do use these shortcut formulas, it is important to sketch the vector to make sure that our angle theta is in the correct quadrant. Here's our magnitude, and here's our direction.